morning, Durvesh, Suharsh, Tejas. 3 boy students today ranked first three of the first three. Manasi, Kirti, good morning. Yuga, good morning. Anjali Kumari, good morning. Praveen, good morning. Avinash, good morning. Ritesh, Mitali, and Asmita, good morning to you all. Vikrant, Nitin, and Prachi, good morning. Bini and Devarishi, good morning to you all as well. And Anuja, Kalyani, good morning to all of you all. Before we start, I think many of you all must have been following. I am a Dan or a dead fan, I would say, as far as Indian cricket is concerned. And yes, good morning, Pooja. India has won the second test match, also called as the Boxing Day test match. It's called as Boxing Day basically because it starts on the 26th of December in Australia. And with the type of defeat we had last time, Ishwari, good morning. It is very commendable that they have struck back. Akshay, good morning. And they have won the second test match. Let's see what happens with the third test match. Anyway, well played India, Team India, I would rather say, and a good captaincy Ajinkya Rahane. Sheetal, good morning. Well, we have done a lot of basics about Isostacy yesterday. What I'm going to do today is I'm going to go deeper into Isostacy today. Chaitrali, Gaurav Kumar and Chaitrali, good morning. And the purpose I have shifted back to StreamYard is because I could not, Ashutosh, good morning. I could not record it yesterday, and that's the very reason I'm going to revise a bit of it with you all so that we have it as a recorded segment. Chinmay, good morning. As a consequence, let us not waste much time because it's going to take time as when it comes to putting all of this together. And thus, let me share the theory as such. As said earlier, a few things that I would be repeating would be the term isostacy was coined in 1889, I suppose. If I'm not placed this, just give me a couple of seconds. Yeah, it was around 1889 by Dutton or 1859. I'm not very sure, but Dutton is the person who coined this particular word based on various terms like isostasios or equipoise, that's balance. Okay, what it means is that objects tend to be in balance. I'm saying objects because I'm still in physics. I have not come back to geography. Objects stay in balance with regards the density that they are made up of, and of course the density in which they are supposed to be there as such. Why density is important as far as isostasy is concerned? Basically because when we studied the interior of the Earth, if you remember, we saw that the densities, the layers of the interior of the Earth are basically separated on the basis of their densities. And depending on the density and pressure as such, we had different, I would say, forms of matter as far as the interior of the Earth is concerned. Like the core of the Earth to start with is solid, and the outer core is liquid. And then you have the mantle, which is solid, but then the upper part of the mantle is semi-solid or semi-liquid, or should we say plastic as such, because it is seen to move convectionally. And then you have the crust. Okay, now comparatively, you'll see that the crust is the most thinnest of the layers, which is further divided into two parts. And as far as this crust is concerned, it is not more than 50 kilometers. Okay, some believe it's just 30 kilometers, but let us average it out to 50. And the lithospheric plate is 50% of the crust, and the rest 50% is the upper layer of the mantle, also called as the asthenosphere. Asthenosphere basically meaning a plastic substance as such. The heat generated within the interior of the Earth keeps on moving convectionally, and I don't think I need to go into explaining what exactly convection means as such. Then this variety of densities is called as the interior being made up of differential densities, and I've already said that the crust is the thinnest of it. Add to this another aspect of rotation and revolution. Here again, we need to bring in a few things about relativity again as such. Okay, though rotation and revolution do affect these things, or rather, it is based on more on rotation because of the fact that revolution, though a curved path, you'll see that this path is a very gentle curve of what 942 million kilometers in circumference as such. So how much that the speed of course is there, but that how much that affects these things happening, isostasy happening, is something that can be discussed further. But rotation, yes, okay, you'll see that if 44,000 kilometers is the speed at which the Earth moves along the equator, of course it goes on decreasing as you move towards the poles, and at the poles it is just a twist around itself. Okay, because the pole is a point, it is not a latitude. We have discussed this also in an earlier lecture as such. So it's rotation that makes this angular velocity and momentum, and that has to be controlled with regards this whole equation of isostasy or equilibrium is concerned, because along any angular movement you are going to have two forces that need to be in balance, the centripetal and the centrifugal forces as such. Having said this, we yesterday spoke about the fact that yes, this is not a theory basically of geography. Its implications are in geography, but it has more of physics, and it has more of mathematical calculations. I have a few slides which we did not see yesterday, which speak about these mathematical calculations. I am a person who is very scared of mathematics, so I will not go into the details of explaining those, but I'll put the PDF of this particular PPT in our group, so those who are so to be the mathematicians of tomorrow can look into that, and you can post explanations to that in our WhatsApp group as well. Um, the implications, as I've said, of this particular theory, though it belongs a lot to the explanations are more about physics and mathematics, the implications can, of course, be made in geography as such. As I said, relativity is something that we need to keep in mind when we are actually going through this particular theory. Let me tell you, it is not the theory. We have said this yesterday also. It is not a theory of crust building. Okay, neither it is it's a process, or neither is it a force as such. It is something which happens in the process of balancing based on physics as such. And more to say, unlike the theories of Wegener and say Joly and Hess, and eventually the plate tectonics, wherein you have the crust moving horizontally, you'll see that isostasy is where the crust moves vertically up and down. So these were a few basic things that we have to keep in mind when we go into understanding the theory of isostasy as such. I'll take you back to the year 1735, and the French and the Spanish, they sent out expeditions to measure the circumference of the Earth, okay, to confirm the curvature of the Earth and measure the circumference of the Earth as such. And when in South America, they split into various directions, and the French of them, who Perry Bourget was a part of it, and he was into this expedition of trying to measure the density of the Andes Mountains, and given the height and of course the volume of the Andes Mountains, it was believed that they should be very, very dense as such. But that plumb bob experiment, we are going to just see it again in the slide. We are going to repeat a few slides of yesterday as such. saw that the bob was not actually pulling, or the bob was not actually pulled to the Andes Mountains as it should have been. And something similar to this repeated itself in 1854 with reference to Sir George Everest. Okay, he was into the trigonometrical and geodetic survey as such. We'll come to that in just a moment. Isostacy, we have said about it yesterday as such that it is basically a comparison between different densities, and the best comparison could be between lead, one of the heaviest, and wood, which could be comparatively lighter. As such, the density of lead you can see is 11,000, around 11,000 kg per cubic meters, and this is just 750. Okay, so it's not even 10% of the density of lead as such. So what makes up 1 meter by 1 meter and 1 meter of cube, the weight is going to be around 25,000 pounds, or say approximately 12,500 kg as such. Requires a proportionately larger amount of wood, which would be 2,000 to 2,400, sorry, 2.473, that's 2.5 cubic meters, to get to that particular weight as such. So this is what was being explained, and now when we speak about the same thing in so-called the rocks which make up the crust. Okay, of course, the heavier of the rocks is basalt, and the lighter of the rocks is granite. This example, the earlier one, was just to make us understand how density plays an important role as such. Okay, because here you'll see that the density difference is not much, but yes, there is still some amount of difference, which is not shown in the diagrams, but yes, you can see that this is 1 meter by 1 meter by 1 meter, and this is 1 meter by 1.06 meters as such. So you'll require more of granite in volume to equate it to the amount of basalt as such. So thus the word has its meaning in Greek roots, and it's this means pressure at the base of various parts of the crust is equal. So if the crust types are different densities, then they have to have the same pressure beneath, means the thickness of the volumes must differ. Okay, and this is what we also have seen yesterday. And as far as this aspect is concerned, I'll just explain it to you once again as to the basics of it. Okay, you'll see that the density of water, which is the base density, 1,000 kg per cubic meters. When you compare it to water as such, okay, it is 750 kg per cubic meters. So what happens is, if you take a log of 1 meter by 1 meter, 1 cubic meter, it will so happen that in proportion to water, the density in proportion to water will go down 75%. Now, because this is 750 kg, this will go down 75%. Okay, that means that given that the water density is higher, the water displaced by 75% of the log is enough to float it here. Okay, as I said yesterday also, that if these had been equal, the water, the log would have just submerged itself to the level of the water as such. And of course, it would have been of a higher density, it would have sunk down. As the density of this wood probably would get lesser and lesser, the amount of log that would rise above the water will get more and more and more. Okay, which means that in the present circumstances that you see in front of you, oak is only 75% dense as water, and that is why only 75% goes down. Okay, something that we should have done yesterday, but anyway, it doesn't make much of a difference. You'll see that when we cut different logs of oak, okay, because this is what came first. This is what came first, and called as George Airy's flotation theory. Okay, what I do is in a water density of 1,000 kg per cubic meter, I immerse logs of different sizes. Okay, I immerse logs of different sizes. Sizes in the sense the length, the breadth is the same, but the height is going to be different. Okay, so you'll see that the longer the log, of course, the deeper it is going to go, and a proportionate amount, that's obviously going to be 25% of the thickness of each of the block will of course stick out. Okay, so thinner the block, lesser is going to be the amount of wood above water. But having said this, it's going to be 25% of the total log, because the log's density is 750 kg per cubic meters. Now, this is a very simplified version as compared to what is happening as far as the crust is concerned. Very, very simplified, I would say. And what followed later is this, that you're going to have different densities, and accordingly there's going to be different amount that's going to be up and down. And you'll see that they took 4 different wood varieties with a variety of density, as it's ranging from 130 kg per cubic meters, which is going to be the least, to 880, which is going to be the heaviest of this. And in fact, let me tell you, ironwood is heavier than this. If you search for this, not found in many regions, but you'll see that it sinks in, it literally sinks into water as also as such. Then, if we are demonstrating isostacy, the base of the floating wood block must be at the same pressure as the water is at that point in water. Here, we see wooden blocks of varying density. That's the B diagram. Isostacy clearly shows that lower the density material should project higher densities. Now, this is going to help us when we are going to go into understanding the geography of isostacy as such. Higher density blocks sit lower in the water than the low density ones. And the third case, the proportion of the block projecting is always going to be the same for a given density as such. And here we come back to what Sir George Everest was up to. And yeah, it was in 1853 that they were working this, and there were these 2 places called as Kalyana and Kalyanpur, which are in present Uttar Pradesh, and they were doing this trigonometrical survey. And yesterday we went into the details of this as well. You'll see that this is the weight tied to the string. This is called as the plumb line, and this is going to be attracted toward the center of the earth. And this helps us to stabilize this, make this instrument in a single plane as such. Okay, so you'll see that as far as astronomical thing is concerned, what happens is we define our directions with reference to this. That's the North Star, and you'll see that when I am nearer to the equator, the angle of the center of the earth, the surface, the point on the surface, and the North Star is concerned, it's going to be the least at the equator. And as I move away along the latitudes, from lower latitudes to higher latitudes, the angle goes on increasing, and at 90 degrees, actually it is going to be an angle of 180 degrees. As such, it's literally going to be a straight line as such. So keeping this in mind, let us move ahead. Okay, now what exactly do we mean when there's this whole query and this whole experiment of Kalyana and Kalyanpur was disturbed Sir George Everest as such. Okay, survey errors, and just let me see if it is clearer if we put this up here. Survey errors in India were first attributed to the gravitational attraction, of the high mountains. The calculated deflection is, however, greater than the measured plumb line deflection as. Okay, what was mathematically calculated was that the Himalayas should be pulling the plumb bob towards is. Yesterday I showed you how relatively, if you're going to place heavier bodies, okay, remember that the surface of the earth and any body on the surface of the earth is obviously going to be nearer to a relative body nearby it as compared to the center of the earth. Okay, so what is going to happen is the plumb line deflection caused by the combination of excess of mountain mass of mountains plus less mass than expected below the mountains. Okay. Now what happens is, okay, if you have this particular tripod standing here and you have the plumb line, okay, of course this is an exaggeration of that. Okay, you have the plumb line dangling down. Okay, it is supposed to be moving towards the center of the earth. Now that you have the Himalayas, which is heavier, okay, and heavier to this point as such, we are believing that this is very heavy, and as a consequence, we expect the plumb bob to shift significantly towards the Himalayan mountains. Okay, expected plumb line deflection by gravitational attraction of the mass of the mountains is 0.0044 degrees as such. However, actually the plumb line did not deflect to that particular thing, which explained that the mass of the mountains was lesser in density, and this resulted into a deflection of only 0.15 degrees as such. So the mountains don't have a excess mass. In fact, they have a deficit mass, and that is done to balance out these things as such. Now, another interesting aspect, you'll see that uh, initially what George Airy was saying, I'll come to it one by one. What is George Airy trying to say? Airy's isostasy, in which a constant density crust floats on higher density, the diagram of all oak logs as such, let us remember that. Okay, and topography is determined by the thickness of the crust as such, the thickness of the crust as such. He said that, say for example, now this is a plateau, this is a plain, this is a lower plateau, this would be a higher plain, and this would be a lower river plain as such. Now, if we are expecting these to be at above the mean sea level as such, I forgot to put the mean sea level into this. It is expected that a proportionate amount of it goes deeper. These were called as the roots of that particular system as such. Okay, these are supposed to be going deeper. Okay, you'll see that this thing here, I'll just, okay, this is the root. This is going to be the root. Okay, for that substance to be stable for thousands of years, obviously there needs to be a balance in it. And he said that the roots need to be deeper. The major contradiction or criticism to this particular theory was that, okay, if you say that only one third of the total amount, or one part of the total amount is standing above, given at this particular density, if we assume that 8 parts out of 9 parts are supposed to be used up as roots of that particular system, and if we see, or rather we know, that the Himalayas are 8.5 kilometers, 8848, isn't it? 8848, 8850, and now they say it's 86 centimeters more. But at least we can, all of us can agree, whatever the height in difference in centimeters, but it is 8,500 meters tall. Now, for 8,500 meters to solve, that is 8.5 kilometers, you need to have equal amount of base here. The criticism was that if we consider this line here, if we consider this line here to be the root of the Himalayas, it's going to be into 8 times, isn't it? So 8 kilometers into 8 kilometers, that's going to be 64 kilometers on a very rough average, 64 kilometers. Now we are saying that the crust is not more than 40 kilometers, maximum 50 kilometers. So you'll see that the roots would travel into the mantle, and having traveled into the mantle, the pressure would melt it. Having melted, it is going to defy the law of the iceberg flotation, the law of flotation, that one part of every 9 parts stays above water, provided a particular type of density, and the rest of it is just below that as such. Okay, so what we mean to say here, or what we mean to observe here, is that it is not possible as to what Airy was actually trying to postulate as such. But you'll see that Pratt. He used this concept in a different way. And who is Pratt? Archidonian Pratt is basically again a mathematician. Airy was George Airy was basically an astronomer with the Royal Society of England as such. He when there was a lot of he put forth his flotation theory, and he said that the continents are basically who this guy. Huh? We'll come to Pratt in just a moment. He said that it's all about flotation theory, and you have continents made up of seal, and the substratum, which different people later on identified differently, is the Saima. He says roots of these continents are basically deep into the Saima, and when we say both Sial and Saima are not more than 40 kilometers, his theory was basically to face a lot of criticism because of all these facts as such. So while this was happening on one side with Airy, this whole issue about the problem of Kalyana and Kalyanpur in India was referred to Archidonian Pratt, who was a mathematician, by George Everest, and he said that okay, if this is a problem, the flotation is going to be a problem, then let us look at it from a different perspective. For a simplified model shown in the new density is the height of the mountain, and C is the thickness of the crust. In the sense, see this here, what he means to say is, unlike here when the densities are the same, he says that it's not the densities that are same, it's the density of the substratum which is the same, and the density of these is going to be different, and taller the substance or the feature. Substance in the sense, if you are doing an experiment in a laboratory, taller the substance standing, obviously lesser is going to be the density, and shorter shorter height, more is going to be the density, is what Pratt had to so he said that you have densities, higher columns obviously are going to have lower densities as such. And now let us look into uh, what Airy and Pratt together had to say as such. So you'll see that this is the mantle, and we know that the density of the mantle is 3.3. That means 3,300 kgs per cubic meter. As such, continents are above but lower of density. Okay, please try to understand this. Okay, continental crust is taller, so obviously it needs to have a lesser density. Oceanic crust is shorter, so and the reason it's shorter is basically because it has a higher density. Okay, we equated this into basalt and granite, if you remember this. Now, if this thickness is 35 kilometers and this is 7 kilometers only, okay, you'll see that this difference of 5 kilometers elevation is basically balanced by the difference in density, is what Airy and Pratt actually were meaning to say. Okay, both of them were meaning to say the same thing as such. Okay, now there is an interesting aspect that we need to remember here. Yesterday, if you remember, I said that if 7 billion of the human population or at one particular point of time says that okay, we are going to jump and jump and jump, and let us see if the crust, if you say that the crust is floating, okay, then the increase in the weight of the crust because of all the 7 billion human beings jumping on the crust, there should be they should shake up the crust as such. Okay, but it is not easy as that. Okay, you'll see that if T E, okay, is basically the thickness of the substratum, and lambda, let us call this lambda, is basically the width of the object that is floating in the substratum. If TE, that's the thickness, is going to be more than the more than lambda, no isostasy. Okay, now if we reduce this thickness to less than this or proportionately equal to this, you're going to have regional isostasy. That means you'll see that the Himalayas will shake up only that much area. It will not affect southern parts of India as such. If this is further less and lambda is more, furthermore, okay, this is the viscous asthenosphere as it is said here, you'll see that you're going to have regional isostasy, and it's going to be very, very small here. The thickness is going to be very, very small, and the feature is going to be comparatively larger. As such, you're going to have localized at that particular point itself. You're going to have examples of this in just a moment's time. As such, okay, so that is how it operates. Okay, that the thickness of the feature needs to be significantly large when you are supposed looking at it as far as thickness of the substratum is concerned. Okay, so the floater has to be large enough to cause isostatic equilibrium as such. What are the tectonic impacts as such? Okay, shortening and stretching of the crust by compression and tension have effect of the changing local crust thickness. Thickening raises the crust as it is the proportion of the exposed crustal thickness that is constant. In similar fashion, a thinning of sorry, I'm very sorry that you are not able to see the text matter. I'll post the um, PDF of this. I tried to build this up in number, but it is not showing to you. Anyway, I'll try to explain it in diagrams as such. Okay, now you'll see that what happens. This is the initial crust, the continental crust, and this is the mantle. Okay, now what happens is the crust thickens. Okay, and you'll see that it tends to rise. The root, you'll see that you'll have a proportionate root here as such. Why is the crust thickening? Basically because the plates are moving into each other. So the crust is thickening, and this is very similar to the Himalayas forming, let us say. You have the Indian plate from here, and you have the Eurasian plate as here. And the Himalayas are rising here. Because the Himalayas are rising here, you'll see that the roots tend to go deeper as such. On the other hand, you'll see that the Rift Valley of Africa, as I was speaking about, okay, you'll see that when two um, plates are moving away from each other, what is happening is the crust is thinning here. As the crust thins, you'll see that it falls lower than the average level, and because of that, the thinning of the root decreases as well as such. Okay, so this is what is happening here. Okay, this is land part, and of course, then you have the continental shelf part. Okay, you'll see that as it goes on thinning, okay, the thickness of the substratum goes on decreasing as also as such. Okay, this is how we can explain it as such. Okay, then what actually happens on the surface before reading into it, or rather I will not read it basically because you are not able to follow me because of the font is not proper. Okay, I'll tell you. Okay, now what we have done is we have taken two blocks of equal size, and this is actually the geographical explanation of isostacy, that you have taken two blocks of equal size, block A and block B, same elevation, same density, etc. Okay, now what happens is on one block you start scraping this. Okay, you must have seen this instrument with a carpenter. He tends to polish off the surface or equate the surface as such. Now, this hand is supposed to be an agent of erosion. It could be a river, it could be a glacier, it could be wind, anything. Okay, you'll see that this agent of erosion is now trying to uh, erode the surface. And as this is being eroded, now what actually the carpenter is doing is he's shaving off the wood shavings, and he's putting it on block B as such. Okay, so what is being eroded from here is being deposited here. What happens is block A is now going to be lighter, and as a consequence, block rises as the weight is removed. On the other hand, where is this weight put on? This weight is being put on block B. Okay, so because it is being put on block B, the wood shavings have their own weight, and they will be a cause for this this block to sink further as such. Okay, now what was at equal depth here is in fact separated now. Okay, this is lighter and gone up, and this is heavier and gone down. This operation and all is called as maintaining isostatic equilibrium as such. Okay, as I said that a small mountain, okay, you'll see that if it is smaller than 100 kilometers, okay, you'll see that it will hardly make an impact as far as isostatic equilibrium, regional or local, is concerned. It has to be sizably large as such. Okay, this lithospheric flexure, we don't have to go into the details of that. This is the most recent of the theory as far as balancing out things in the mantle is concerned as such. Okay. um, you see what happens is when you have a weak crust, and let us assume, I'm going to give you an example of this. You have a lot of glaciation that takes place in a particular area. As a consequence, this starts going down. Okay, when you have a strong crust, what happens is the glacial ice melts, and and a long time later, what happens? You see that you have subsidence here, and around you have upliftment. Okay, so you'll see that the depth remains the same, but the crust being strong, okay, the weight has increased, so relatively this will go up. Okay, here what has happened is this has gone down. Okay, now what happens after the glacial ice melts? This glacial ice melts, you'll see that it is going to rebound here. On the other hand, when the glacial ice melts in in a stronger crust, sorry, you'll see that there is going to be a subsidence here and a upliftment towards the central part as such. This is in fact what is called as the flexural theory. Okay, it keeps on, the crust keeps on flexing itself depending on the regional crust being I would say strong or weak as such. Okay, now this is glacial isostacy. Now this picture here is about these Great Lakes. You can see the Great Lakes in the background here. Okay, and you have the Hudson Bay here as such. Now, it is believed that in the last glacial age, you did not have anything like the Great Lakes here in before the glacial age, is what one theory hypothesizes as such. What happened is you had a large glacial ice sheet here. Now, because there was this glacial ice sheet, uh, it pressurized the northeastern part of the North American continent. Now, after the warmer times came back, what happened is the southern part of it, okay, it started melting faster because it was nearer to the equator. So it released a lot of water as this, but this northern part was still solid. And as a consequence, what happened is this water was released here and it accumulated in these lakes. Okay, so it is believed that the Great Lakes and of course this Hudson River, okay, and this seaway, St. Lawrence, sorry, this is the St. Lawrence Seaway here, and this is the St. Lawrence River. This is the Lake Erie, Ontario, Michigan is here, Superior, and I forget the names of the others as such, but that is how the water accumulated here, and the ice kept on retreating and the water kept on accumulating, and then you had the formation of the Niagara Falls, which is going to somewhere here, and the water, instead of going back this way, it found its way into the Atlantic Ocean through the St. Lawrence River as such. Uh, now, before we go further in understanding this, I will be using one of these. Yeah, I will be using this diagram to further say what or the further developments as far as isostasy is concerned. Before that, remember what Airy says is uniform density, uniform density, uniform density, and varying thicknesses. Varying thicknesses. You'll see that the substratum doesn't matter. Varying thicknesses, okay, and uniform density. What Pratt says is uniform depth. Uniform depth. Okay, all of them have stabilized here with varying densities. The densities are different, is what Pratt says. Now, there were a couple of scientists who believed a lot in Pratt, Hayford and Bowie, Hayford, and Bowie is Bowie. Both of them were Americans, and they said that, okay, what Pratt says, this level, okay, where all these densities stabilize, this is called as the level of compensation. Okay, this is called as the level of compensation. Now, there was an error here, but I'll come to that error later. They said that at around 100 kilometers of depth, and that is how This 100 kilometers is used in plate tectonics as the thickness of the lithosphere. Is because Hefford and Bowie, they said that all this dense, all these variety of densities, they balance out each other at a depth of around 100 kilometers, and that is what they called as the level of compensation here. But subsequently, you had John Jolly. Okay, John Jolly, who is the one who gave us one of those theories in between um, Wegener and plate tectonics as such. He says that it cannot be a level of compensation basically because the Earth is a sphere and in 3 dimension, it would be very difficult to have one line along which you're going to have all these balancing as such. So there is going to be a transition phase. There is going to be a transition zone, and instead of calling it as the level of compensation, you'll see that John Jolly calls it as the zone of compensation. The zone of compensation. Okay, so you'll see that all these is basically an explanation of a lot of physics and a lot of mathematics as such. What are the implications that we are supposed to be seeing as far as geography is concerned as such? Okay, you'll see that this is the one I was referring to, how they have used a lot of mathematics and physics into this, and it would be difficult for me to explain this. Okay, you'll see that if this is the continental block, I'll explain the geography of it. Okay, those doing physics and mathematics can go into the respective subjects of this. Okay, it's very self-explanatory, but I am incapable of explaining all these equations as. Okay, you'll see that if this whole thickness is balanced at this, a deeper continental crust will make a topographic surface to arise up, and a shallower continental crust will be compensated in this particular way. So the mantle will rise up here. Okay, is one explanation that you have, and then you have another explanation here. I will obviously not go into the details of that as such. What are the implications that we are supposed to be having? Basically, as far as these implications are concerned, let me see if you are able to see this font that I am trying to display. Let me, okay, if I enlarge it, if you are able to see it, that would be fantastic, and you could read, because this is the geography of isostasy as such. Let me see if we are, yeah, we are able to read this. So when large amounts of sediments are deposited, okay, they remember the diagram of the wood shavings as such on a particular region, the immense weight of the new sediment may cause the crust below to sink. Similarly, when large materials are eroded away from a region, the land may rise to compensate. Therefore, as a mountain range is eroded, the reduced range rebounds upwards to a certain extent. And that is why we say that the Himalayas, in spite of being eroded for so many hundreds of years, are still supposed to be rising as such. Some of the rock strata now visible at the ground surface may have spent much of their time in their history in the sense geological history, at greater depths below the surface, buried under other strata to be evenly exposed on those. Now, this is one thing, one geographical explanation of all those isostatic movements that are happening. You're going to erode from somewhere, you're going to deposit somewhere. From where you have eroded, you're going to have a rebound. From where you have deposited, you're going to have a subsidence. That's one thing. Then, how do we relate it to plate tectonics? Sorry. Okay, we have seen that when plates are going to collide, there is going to be an increase in the density of the crust, and thus you're going to have rising as such. On the other hand, the diagram that we saw, that when the plates are going to go away from each other, it's going to be thinning up. So you'll see that the moment it's going to be thinning up, okay, you'll see that it is going to be compensated from down as such. When continents collide, the continental crust may thicken at their edges in the collision. If this happens, the much thickened crust may move downwards, okay, rather than upwards, as far as the iceberg analogy is concerned, the idea of continental collisions building mountains up is therefore a rather simplification. Instead, the crust thickens, and the upper part of the thickened crust may become a mountain range. Okay, that is how it's easy. Of course, this is a very easy explanation to that as such. Some continental collisions are far more complex, and the region may not be in isostatic equilibrium. So this is subject to, so this subject has to be treated with caution, of course, is what they say. Mantle convection. Okay, perfect isostatic equilibrium is possible only if mantle material is in rest. However, thermal convection in the present mantle is present in the mantle. In such case, only the more general hypothesis of the deep dynamic isostasy can be said. These are the advanced stages of explaining isostasy with geography as such. And the ice sheet theory that we speak about, the formation of the Great Lakes, it can be found in front of during a glaciation phase. What happens is you have a crust here, and you have the glaciers which come and settle down on this. The weight of the glacier is going to push it down, and when the glaciers are going to melt in a post glaciation period, there is going to be a rebound, which is seen even today in the Hudson Bay, the northern part of what is called as the glacier of the North American continent as such. Okay, so the bound and rebound is basically the process of equilibrium that takes place in it as also as such. Okay, and then relative level of sea change. Okay, the sea level change is also very interesting because it goes with climatic change. And basically, when we are seeing sea level change, it's the rise and fall of the water levels. Why and how does the water level rise and fall as such? Okay, as I said earlier, that if you're going to have glaciation, what is going to happen is the water from the oceans is going to be used up. So when the water from the oceans is going to be used up, and this is going to be transferring itself on land surfaces, the oceans are going to get lighter. Okay, and there is going to be a rebound. On the other hand, okay, on the other hand, a recent development shows that if the water is going to absorb a lot of carbon, okay, it's going to heat up, and because it heats up, you'll see that there is going to be a thermal expansion of water. Because there is a thermal expansion of water as the Earth's mean temperature increases, it will show that the volume, okay, or rather the weight of the water will increase, and that's why you'll see that it will press down the oceanic surfaces as such. And then you have the another implication in the lithospheric asthenosphere boundary. The hypothesis of isostasy is used often to determine the positions of a lithosphere, asthenosphere boundary as such. You'll see that more the weight it will go down, you remove the weight it will come up. This is basically the isostatic equilibrium as such. Okay, now this is in short what we were supposed to be explaining this. Now, Karthik, and later. Okay, now, if you have any questions as such, you can just type it down because I'm done with my theory of isostasy. Remember, the core things that you have to understand about this isostasy is that this is the movement up and down, and this is not movement sideways like the continental crust one. This is to do with the density. Okay. Okay, Mayuresh has come up with a question. I'll just take his question and then we'll go back to answering. Sir, I have a doubt. In Pratt theory, in the diagram, as their densities are different, then the higher density material should go deeper. Yeah, I do agree with what you're saying, but if you had say understood what he had hypothesized as such, is that at a particular level, they cannot penetrate further. As a consequence, they have to compensate it by growing taller. Okay, they have to compensate by growing taller as such, because at the level of compensation, and that is why you'll see that later Have Hayford and Bowie, I suppose, calls it as the level of compensation, and Jolly calls it as the zone of compensation. Okay, now I agree with you that it's not it should not have been that way. Basically, you'll see that to make explanation simplified, what they do is that they have drawn lines with using a scale. It is not as geometric, but you'll see that when I, instead of using the line of compensation, I use, or level of compensation, I use the word zone of compensation. The zone is going to be a few kilometers as compared to the 6,500 radius of the Earth. Okay, the zone could be 5 to 10 kilometers, and there could be a bit up and down, a bit. But all of these densities, heavier and lighter, all of them have to be compensated within the zone of compensation, within the zone, because it doesn't allow the roots to go deeper. And that's why the compensation is on the other side, which is open. Okay, so that is basically what I can give as an explanation is concerned. Om has says that, can we say that the Himalayas is not dense because it is still rising? You see that any mountain is not dense. Whether it is rising or not is comes later as a part of isostatic equilibrium. Okay, anything that is taller, okay, is going to be less dense. Anything that is shorter is supposed to be high dense, more density. And then this is what isostatic equilibrium is all about. Well, as I said, major things that you have to remember, that this is not a geographical theory. We are actually using Saket has come up with an interesting question. I'll just answer that later. And let me finish with this. What was I saying? This question disturbed me. Anyway, I was referring to, yeah, understanding all these things. You'll see that the Earth is rotating, and this rotation is causing the variation in the interiors, the mantle, and so on and so forth. And the crust is very, very narrow. So these are adjustments. Okay, but these adjustments are taking place at a very, very slow pace, vertically up and down. They're taking place at a very, very slow pace, let me tell you. Okay, it's not as easy as taking water and putting a plastic toy or wooden blocks in that and just pushing them down and you see them rebounding. Okay, it's something that happens very similar to this, but it's many times exaggerated as far as the speed is concerned, because your substratum here is not water and it is a denser material. This is going to take a hell lot of a time. This is going to take thousands of years. This is going to take millions of years to happen as such, but principally it remains the same. So it's explained in physics and mathematics, but it is experienced in geography as such. Okay, so and because it is somewhere related to thinning of the crust in plate tectonics, people tend to relate it to that. But let me tell you, isostasy is different, and the crustal formation and horizontal movement of the crust is different. Okay, eventually the earth whole is a system, and as a consequence all of them are linked, but the operations are happening at individual levels as such. Okay, so I hope you have understood this, because as a student, I am frank to admit it, that as a student, it took a lot of time for me to understand what actually isostasy was. Looking back today, I say that I tried to link it to the crustal theories from Wegener all the way to plate tectonics, and that is what I believe confused me more as a student. As such, okay, you have to look at it objectively, individually, these theories objectively, individually as such, and thus understanding then becomes easier as such. Now, this was the interesting question. What about reopening of the college? Saket Shinde, your spellings are horrible. Well, it is believed that 4th January, 5th January onwards, things should start. If there is no spike in corona cases, this particular UK strain as such, 15th, around 15th, there should be some movement. I'm not committing anything. These are my personal opinions. I'm not committing anything as such. So around 15th, there should be some movement as such. And if things still continue to improve, there could be new guidelines from the center, from the state, and from the local government. That's the PMC. Okay, it will all depend on how these three tiers of government, they respond to what is going to happen in the next 15 days as such. Okay, so fingers crossed, let us believe that things should run fine. And having run fine, we could see that the colleges possibly, fingers crossed, possibly could start in the month of January as such. Uh, but sir, you already said that in airy theory, the root of the Himalayas is deep down in stuck. That's where Airy went wrong, isn't it? He was criticized because of that. I did not say this. Airy said that, and he was criticized because of the fact that if he says that Himalayas is one part of the nine parts, okay, the rest of the 8 parts is going to be into eight. So 8 into 8, 64 kilometers goes much beyond the limit of the crust, and that is why Pratt had to come up. But as I said, that Airy had its problem. Similarly, Wegener also has his problems with his theory, but they give you an insight, and that insight is developed further upon to explain the same phenomena in a modern sense as such. So anything that is wrong at an initial stage should not be completely discarded. There could be something which is valuable out of that particular experiment. Okay, so it is always said in science that when an experiment fails, this does not mean that the person is wrong. Okay, there could be some part of that experiment which has not worked. Okay, because when you perform an experiment, okay, you have some hypothesis, and you try to go along with that particular hypothesis as such. Okay, some process tweaked here and there could straighten up your experiment, is what was shown as to how Pratt used Airy's concept to basically prove the same point, but in a different way. You put the same thing in a different way, you get an answer to a possibly question which was not uh, answered. Akshata says that it's a bit hard to digest both the theories. I'm not asking you to digest both the theories, Akshata. Okay, what I'm saying is Airy was a start to what Pratt innovated on that particular start to prove his particular point. You don't have to believe both the theories as such. In fact, the criticism is so valid about Airy that you don't have to. But as I said, that when we speak about crustal movements and plate tectonics, you cannot let aside Wegener. Though there are so many criticisms, but the original thought by Wegener is what led to the present theory. So similarly, you'll see that the original thought of what Airy says is how Pratt uses his mathematics and all those other things. I'm going to post this in the group, and if anybody can explain further in the mathematical sense, it's fine for us. So that is what I'm saying. That is what I'm saying, trying to say, that you don't have to believe both the theories. Okay, the first theory is partially right. It has more of criticism. Okay, Pratt extracts the criticism out of it, and he innovates into his own theory of the level of compensation or the line of compensation, from line to level. And then of course Jolly says it cannot be a line, it cannot be that geometric, it has to be a zone. So it is going to be a bit up and down at that level also. Okay, and of course, as I said, it's not very geometric, as we have all these diagrams that we have seen. Okay, you'll see that no feature, you go around and no feature, no mountain is that geometric as such. Let us see what Saket has to say. We can add this to the assignment. Yes, if you can do this as an assignment, it could be fantastic. In fact, we could, if it turns out to be a very good explanation, we could actually pass it on to the students also as such. That's a very beautiful thought by Saket, that he could add this to his assignment also as such. So that's all that we have as far as questions are concerned. If you don't have further more questions, I could be stopping our lecture today. If you have any queries further, you could of course post these queries into our group as such. Let me again admit that mathematically I'm not that strong. So you ask me to prove it through equations, I would not be able to. Ask me the geography of it, I will give you a lot of examples as this, but mathematically I will not be able to. I'm still at this age, I'm still scared of some aspects of mathematics as such to frankly accept that flaw as such. So if we don't have any further questions, I'm ending the broadcast right now. See you next week.